Stop my video. All right, so let's do this as a warm up, and let's answer these two questions here. All right, the first and on Friday we're gonna do kind of like I'm gonna use these breakout rooms in Zoom, and we're gonna do kind of like a breakout question session where I'm gonna give each group a question to work on, and we'll come back. You'll present it, explain it, and then whoever's in your group, in your breakout group, when you explain it, if you get it right, then everybody in that group is gonna get some points, some bonus points. All right, so we're gonna work on that. But that'll be Friday. So prepare your mind for that. All right. So first question, what reaction is that? And what's the outcome? Now, don't all speak out at once. I know it's Wednesday.
It's the hydroboration oxidation.
Hydroboration / oxidation. Very good. So can you tell me in that reaction what the final product is going to be?
You're gonna get a alkene, and it's gonna be alcohol and 2 hydrogens.
Okay. And then what? That's
The hydrogens gonna be trans of each other, and and one hydrogen and alcohol gonna be cis, right?
All right, hold up. Let me make sure we're on the same page now. So you're saying we're gonna get an intermediate, is that right? I wanna get to what the final product is, but I'm glad you said that because we can work with that. So are you saying you're gonna get something like this?
Not exactly.
No?
Well, yes.
Yeah, that's what you're saying, right? Kind of.
Yeah.
Trans, I heard you say trans and all that good stuff.
Yeah, the 2 hydrogens gonna be trans to each other.
All right. I'll take that. But is that the final product? Does it stay like this? That's the question.
Oh no.
It does not.
Because that's the enol form. Mm-hmm. So the keto form is gonna be 2 hydrogens on the same side.
Okay. So that's what I'm looking for. The keto form. Because the enol form,
okay,
it doesn't stay like this, right? It actually rearranges. Is that right?
It's not stable.
Right. So it's gonna rearrange. Let me see if I can paste it right here. Ooh, artistry. All right. So the final product is the keto form, right?
Mm-hmm.
Let me finish it. So the final product is gonna look like this. Is that right? It's the enol, but the enol is going to rearrange. Shrink that down a little bit. Doesn't the enol rearrange to give you the keto form?
Yes, it does.
Yeah, that's what we were talking about all Monday.
So
sloppy. Sorry. All right. So let me give you a rule of thumb, right? If you start with a terminal alkyne, what that means is that your carbon at the end of the chain in the alkyne, right? You can see it's a CH right here. So that means it's terminal. So the alkyne is at the end of the chain. If you start with a terminal alkyne and you do hydroboration, oxidation on a terminal alkyne, you're going to get an aldehyde as the product, as the final product. Oh, come on, Russell, get your mind right. You get an aldehyde as the final product from a terminal alkyne.
I have a question.
Go ahead.
So I thought it was like for the first structure you draw after the arrow or the like what it's telling you to draw. I thought it was 2 H's.
Hold up. You probably right now. Where at? Are you talking about here?
Yes.
Yeah.
Okay.
You're right.
I'm just making sure.
Mm-hmm. And you're right about them being trans to one another as well. Because see, you got to remember this and this came from the same place, right? The H and OH right there on that side came from the hydroboration / oxidation.
Yes.
Yeah. All right. Yeah, you on it now.
Then you gotta put the H on the other one.
Yeah. No problem. Actually, that one is going to have two hydrogens on it.
Yeah, the hydrogen's on the same side for that one.
Right, because remember when it rearranges, one of those hydrogens, the hydrogen from the OH is going to end up on that carbon.
So what is that on the bottom of the carbon? Is that another H? So it's 3 H's?
Yeah, no, it's only 2.
Yeah, okay.
Yeah, let me just fix it up. All right. Is that satisfactory?
No, because I still see 3 hydrogen. That's what I'm trying to understand.
No.
I thought it was
Three?
only.
She's talking about total on the structure.
Well, one of them was already there, right?
Oh, it just.
Oh, okay. I get it.
Yeah, that was already there.
Okay.
All right. Thank you for the clarification. Was that you, Kayla?
That was
Yes,
Kayla.
sir, it was.
Yeah, thank you for that, for clarifying that. All right.
You're welcome.
You got a terminal alkyne, you're going to end up with a aldehyde. If you do hydroboration / oxidation. If you do mercury catalyzed hydration, which is the second reaction, you have a terminal alkyne, you're going to end up with what? What do you think?
So
Right. Let's think about it now. Use your reasoning skills, right? You know that hydroboration oxidation puts an alcohol on the least substituted carbon. What is the mercury? What's the regiochemistry for the mercury reaction? Where's the alcohol going to be? You know this because we've already done that. I promise you know it. It's right there in your grasp.
I don't
Right?
know.
Oh, yes, you do. For mercury, think about it now. Boron is anti-Markovnikov. Remember that? Bam. And then mercury is Markovnikov. So where should the OH go here? Shouldn't it go on the
It
more
will go right there on that first one.
Shouldn't it go here? Is that right?
Yes.
Right. Because mercury is gonna follow. It's gonna follow the same regiochemistry as it would if I was using an alkene. Right. So then my product, what's gonna happen there? Right now, my carbonyl is gonna be here. What kind of carbonyl is that? Uh-oh, let me get rid of that H now. Can't have a PhD and draw that. That might take it back. It's a ketone. Is that right? So if I use the mercury reaction on a terminal alkyne, man, that is so sloppy, then it's going to be a ketone as the final product. The enol is the intermediate. You're always going to get that. All right. We okay? Y'all got quiet.
Yes, sir. I understand.
All right. Right. So the difference in mercury and boron is the regiochemistry. Remember that term? Right? That's basically saying which carbon in the alkyne does what. You know, where's the OH going to end up? Where's the H going to end up? That's what we mean by that term regiochemistry within that alkyne functional group. All right. Now we gotta do some head busting on this next question, but we can do it. I think we can do it. All right. So let's look at the next question. Hopefully you have this handout. It is there in module 4. All right. So we're gonna this is a kick you know what question on purpose, because everything that we've talked about up to this point with alkynes is in here some kind of way. All right. So it means that we're gonna have to go back and remember let me just give you an idea of what is here. Right. So you got acetylide formation. So acetylides. You have a little bit of alkene chemistry. All right. Ooh, that S is ugly. Sorry. Right. Got a little bit of alkene chemistry. You have some substitution. Come on, pen. I hate writing this word substitution out. I always have to sound it out of my head like a 5th grader. All right, you got some substitution. You have some alkyne reduction. All these reactions in here. Let me look at this. And you have some stupid pen. That's what happens when they cheat. And you have ozonolysis. So all of that is in this reaction scheme. All right, and it gives us a chance to talk about these synthesis reactions where you got multiple reactions happening, right? So let's just take the very first reaction. I'm gonna copy this onto another page so we'll have a chance to write everything down. I don't want anybody to miss anything. So let me do this. I did not pick that. What are you doing? Do what I told you. We're gonna take that, we're gonna copy it. Then we're gonna come back and fill in those boxes with the products. All right. So don't panic. I know it's a lot. That's my job though, to help you navigate this sea of reactions, because it's a lot of stuff. All right, let's take the first reaction. Let me copy that. Anybody here ever had elephant for dinner?
I have not.
Good. It's nasty. No, I'm just joking.
You ate it before?
No, I'm joking.
Okay.
I'm a savage, but I ain't that much of a savage. To eat an elephant. No, but you know the saying, right? How do you eat an elephant? One bite at a time. That's what we're about to do with this problem. We're about to knock it down. One part at a time. And I promise you, by the time we get finished with it, you're gonna feel so confident that you'll be ready to take an exam tomorrow. That's my goal, is to build up your confidence with organic to the point where you feel like you just can't be touched. All right. So let me take that first reaction, I'm gonna paste it right here. Boom. So first question, what kind of reaction is that? We're gonna talk about we're gonna talk about the reaction itself and the outcome. So if I let me, so NaNH2. Shucks. Come on, Russell. NaNH2 is a strong base. All right. Anybody remember what the pKa of the acetylide proton is, which is this proton right here? Anybody remember?
25.
25. Very good. So that means if I have a strong base, guess what? I can pull it off. Is that right? So what am I going to get if I react this alkyne with a strong base? So think about your acid-base chemistry, right? If it's got a pK of 25 and that's my acid, what is the base going to do? So, anybody remember? Proton transfer, is that right? You can hear a rat pee on cotton. It's that quiet.
No, I remember talking about that in the videos.
Yeah, and in class too. A lot. Is that right? So the NH2 is my base, right? That's the basic part of the base. And I don't want to go through the mechanism for all of these because that's going to take too long. Plus, we've already seen this mechanism. Right, this is coming in like that, boom. And we're going to break that carbon, hydrogen. Come on now. Single bond like that. Is that right? Everybody okay with that? And this is called an acetylide. It's called an acetylide. Anion.
Dr. Russell.
Mm-hmm.
So we had them in goal, the same goal as from the last module, like to basically know how to get to the products and know the mechanisms between, like making the flashcards.
Yeah.
Same goal.
Yeah.
Okay.
Anytime you're trying to learn reactions, the goal is to be able to look at the reagents and know what's getting ready to happen.
Okay.
So when I see an alkyne in the presence of a strong base, I already know that that's gonna get do proton transfer with that base and give me this anion, which can be a good nucleophile, or it can be a base. Remember, if you got a primary alkyl halide, it'll be a nucleophile. If you got a secondary or tertiary, it's going to be a base.
Okay.
All right. So that, let me move this over here because I really don't care about this NH3. But I got to show it to make sure everybody on the same page. Get over here like I told you. All right. And let me move all this. I want to rewrite. I want to have to rewrite that. All right. Any questions about the acetylide part? Remember that, Pete, that hydrogen has a pKa of 25. That's not a great acid, but with a strong enough base, it'll come off. And for those of you who are thinking, why didn't I do the other hydrogen? I can pick either one because they both have the same acidity. I'm doing this so we can go from left to right, and I don't have to draw my arrows looking all crazy. So I picked that one. Other side is just as susceptible to proton transfer. All right, look at the second step. What is this? All right, let's draw that out. So the pH is an abbreviation. Let me just put this down here. We're gonna knock these out. We're not gonna be stopped. The pH is an abbreviation for benzene ring, right? We've seen the benzene already, right?
Yeah.
Did I also give y'all that abbreviation too?
The pH abbreviation?
Yes.
Yes, it was like a functional group assignment.
Yeah. So this is a what we call a phenyl. We call it phenyl when it's a substituent. If it's by itself, then we just call it benzene. But when you add it as a substituent, then we call it phenyl. That's what the pH is short for. So we react in the acetylide with, I'm gonna draw it out. This pen is making me madder than the election last night. All right, let's see what we get from that. What do you think? I have a primary alkyl halide and my acetylide anion, which is a really great nucleophile. What do you think is going to happen? I'm going to jog your memory. Is iodine a good leaving group? Based on what we talked about when we studied substitution?
Yes, I think it is.
It's a great leaving group. It's one of the best leaving groups that was on the list that I gave you. So this part of the reaction is a substitution. See how all this stuff comes back together? All this stuff is like, again, now let me jog your memory even further. Which one of those is the nucleophile?
The anion.
Good. So that makes the other molecule what?
Leaving group.
The electrophile.
Mm-hmm.
And it makes iodine the what? Leaving group. So how do I know where to attack with my nucleophile? Think about what we've done this already. How do I know where to attack?
You're going to attack iodine.
You attack iodine or the carbon that it's attached to?
Is it the partially
The
positive?
carbon.
Yeah. You always look for that. Remember we talked about this. You always look for that polarized bond. Is that right?
Yes.
So that carbon iodine bond is highly polarized. That's where your nucleophile is gonna find that carbon. None of the other carbons are reactive, but that polarized carbon iodine bond, that's where your nucleophile is gonna hit. Right? It's just like because remember, what's the rule? Always always flow from what? Source to what?
Sink.
Sink. Right? That is not going to change. I don't care where you take organic. You can take it at Tuskegee, Auburn, Harvard, Princeton, Caltech, doesn't matter. If you know the principles behind nucleophiles and electrophiles, this stuff becomes elementary, right? But that's why you got to practice. Don't tell me my screen is frozen in the middle of my wonderful speech. And it is. God dog it, I'm gonna slap this computer. All right, let me share my screen again.
You try restarting it.
I did. I'm working on it.
Maybe it's just getting old or it needs an update.
I don't think it needs an update. I think it just needs to be cleaned. I think I need to clean my hard drive. I know what the real problem is, though. The processor is trash. That's the problem. Because it's got a huge memory. It's got 700 and something gigs of memory, but the processor is trash. All right. Is that right? Is this what's going to happen? Like that? What kind of substitution is that if it's concerted?
S2.
SN2. Who was that?
Mario.
Mario. I knew you were getting ready to say that. I hate that we're not in a classroom because I'll know everybody by name and face after the first week. But since all I see is my screen and I don't see anybody, I have to remember voices. But we're good. We're gonna work through that too. All right. So what's the product of that sequence? One, acetylide formation followed by substitution. That's what that is, right? We made the acetylide. Now we're gonna do a substitution reaction with an an aryl halide, right? So I should get this as my product. I'm gonna draw it in black. So here, God dang it, ran out of room. Hold up, let me shrink this down some. You son of a gun. All right, and zoom in. So the CH2 is gonna be right here. Everybody okay with that? This is the same CH2 that was right here. I just drew it in skeletal form so I'll have, more room. Any questions about that first sequence? All right, we're good on that?
Yes, sir.
All right. So with that first sequence, you can see right here what A is, right? A right? That's what we just made. We just made A. Are y'all following that? And think about these synthesis problems is that when you see the reagents written like that, come on now. When you see the reagents written like that, 1 and 2, right? What we get from 1, I think we talked about this before, becomes the starting material for reaction 2, right? So we made something that was the result of reaction 1, and then that became the starting material for my second reaction in that sequence, and then A is the final product. Yes or no?
Yes.
So sloppy. All right. Y'all want to go in order?
Wait 1 second.
Yes.
Yeah.
So when
Take
you
your time. Ask any questions. I'm not rushing to get through this. I just want to, we doing it again. We chopping down a tree, piece by piece. So we just hacking away. So any questions you have, ask them, because it's not about how fast we get through this. I will make sure y'all get it.
Okay, I get we took the first alkyne reacted with the top number 1, the reacted with number 2, and you said we get A. You said we get A. Do you mean like the first line of A?
No, look above the A. You see the product?
Yes.
That's what we get from that first sequence of reactions.
Okay, so you just like labeled that A.
Yeah.
And you're gonna react it next with the okay.
Yeah. I mean, A can either go to B or to C. You following?
Mm-hmm.
So that product now is going to be the start material for another sequence. Either A going to B or A going to C. Which one do y'all want to do first?
B.
C or B? You said B?
Yes, sir. I said B.
All right. Well, let's do B. Let's take A. I'm going to copy this. Oh, sorry. I need to apologize to y'all too, because when we first started and I was using this software or this app, and I was not properly using the copy and paste like I should have been. I promise you I wouldn't. And my notes are terrible and jumbled up and all that good stuff. But I learned some things in the process of teaching this teaching this class fully virtual. So accept my humble apologies. All right. So this is gonna give me B. Is that right? Come on. Screen froze again. Oh boy. I think Kristen and T are still sabotaging me. I don't even know why.
Don't do it.
I'm gonna do it. I know y'all over there quiet, like, yeah, watch something happen.
That day that I was talking about your computer, I swear my computer died. So it was
But I don't like ugly.
Mm-hmm.
That's what I heard. All right, hold up. Wipe that out. All right. So now we have A, and now we're gonna use A to make B through this sequence of reactions. So I'm gonna move it. I'm gonna go this way, like so we can keep track of everything. Okay. So what's the first reaction? Hydrogen gas and Lindlar's catalyst. What does that do? Remember, I gave y'all a mnemonic the other day.
Started with the L. Wait, little children always tripping. Yeah, got it right.
So what's the LC stand for? Lindlar's is what? Cis. And
Cis
ammonia is
trans.
So what does Lindlar's catalyst do in the presence of an alkyne?
It can change an alkyne to a cis alkene.
Look at you. See? You see what studying does? Yeah. No, I'm being real. That's what studying does. Right? And so let's do that. So let's take this. Hold up. Let me go back. Make sure we're on the right path. Yeah. All right. So even though this alkene that we get from this technically is not cis because there's going to be a H, two H's on one side. You're right. So we're going to draw it like that. We're going to take that A, this is reacting with one, whatever that set of reactions is, reagents are. We're going to draw out our product. H. But you are absolutely 100% right. I need to put them carbons back in there so we don't get lost in the sauce. And then this is going to be H on that side. And I'm going to abbreviate the pH, if that's okay. Anybody not see that? Lindlar's catalyst is what type of reaction is that? A reduction or oxidation?
Reduction.
It's a reduction. Reduction increases the number of bonds to hydrogen or decreases the number of bonds to carbon. So it's a reduction. All right. So now what? 2 and 3 go together. What kind of reaction is that?
That's elimination.
Okay. Look at it again now. We got mercury acetate and water, which my comma got moved some kind of way. And then we have mercury acetate and water followed by sodium borohydride. What kind of reaction is that? Look at what my starting material is. This is an alkene now. Is that right?
Yes.
And I'm taking an alkene and reacting it with mercury acetate and water, and followed by sodium borohydride. What reaction is that?
Oxymercuration.
Good. It's oxymercuration, which means what? What does it do to alkenes?
It's making an alcohol.
Make an alkene into an alcohol with Markovnikov regiochemistry. Is that right?
Yes, sir.
All right, so here's my product. Let's draw that out. So I'm gonna draw the 2 carbons just like that. Alkene is gone, right? Not there anymore. This is the alcohol. This is the other H that came with it. And then the other 2 hydrogens are here. I want to change the color of that. Sorry. I like using different colors. Right, and then for the other side, that H still there. And then this is still here. Anybody not see that? Or anybody struggling to see it? Say something. Or are we okay? And hopefully you recognize that these 2 sets of reagents go together. Right? Those are your reagents for oxymercuration. Mercury acetate and water in the first step, followed by sodium borohydride in the second step to get rid of mercury.
Yeah, you just showing on the product like how that the reagents can get to cis form, right?
Yeah.
Yeah.
Yeah, because remember, all of these reactions, hydroboration, oxymercuration, they all happen with syn addition. Remember, where the H and OH add to the same face.
Yes.
All right, we're okay with that. So that's B. Go ahead.
I thought you said you was asking a question. We were okay with it. I'm okay with it.
Yeah, so that's B. So up here, where it says B, let me copy. I'm just gonna copy and paste it, and I'm gonna have to shrink it because it's too big. That's B up here, so I'm gonna stick it. Actually, put it right there. Everybody feeling comfortable so far?
So, Dr. Russell.
Yeah.
We basically drawing like the products.
Yeah. Of each sequence.
Okay, but for B you used the sequence of A, right?
I used the product from A.
Okay.
Because I started with this. This is my initial start material.
Mm-hmm.
Then I did acetylide formation followed by substitution to give me A, which is shown above, right?
Mm-hmm.
And then now that product I'm using to make B. That's how synthesis works. You make one fragment and then you keep functionalizing it until you get to what you want, right? So I took the first alkyne to make A, and then that product in A, it's a legitimate reagent, and I can use it to make something else. So I use it to make B, or I can use it to make C. Do we even need to draw C out? What is C going to be? What do you think? Lunch for the first person who tells me.
Acetylide anion.
Okay, that's part of it. You're right. But C is the product. The acetylide anion is going to be one precursor to the product.
Oh, it's you. What was the question again?
What is C going to be?
The product?
Yeah, the final product.
It'll be a transalkene.
Hold up now. You jumping the gun. You looking at D. See, C is in front of the arrow that's going to D. D is going to be a transalkene. You're right, because of the lithium and ammonia. I agree with you 100%. But what about C? Look at the reagents. The reagents are right here. And I'm starting with A. You following?
Yeah, I'm
So
thinking
what?
about it.
Okay. So no free lunches today. That's all right. I'm gonna draw it in there and watch everybody. Oh my gosh, you're right. That's okay. Like I said, we're just chopping down this tree. So C is gonna look like this. Uh-oh, sorry. Is it not? Where I take the other acetylide proton or acetylene proton on A. Can y'all see that? That there's another hydrogen over here that I can work on.
Oh, so are you saying the base attacks the other side?
Yes. Is that right? Isn't the route from A to C identical to the route from here to A?
Yes.
It's the same exact reaction. It's just happening on the other side of the alkyne. Yes or no?
Yes, okay. I
Yeah,
see
it's
it.
the same reaction. But my starting material, instead of it being the alkyne, ethyne, right? It's actually A, which I made from ethyne and then sodium amide, followed by benzyl iodide. All right. So it's the same reaction, but it's gonna happen on the other side. Excuse me. All right. We okay with that?
Yes, sir.
Yeah. So now, Brittany, what is
Yes.
D? You said it earlier.
The transalkene?
It's going to be a transalkene from this starting material, right? Because lithium and ammonia is a way to make what? You go from alkynes to what? Transalkenes. So sloppy. Right? Alkynes to transalkenes. That's what you do with lithium and ammonia. So that product from C to D is going to be, here's my alkene. I got to shrink that down. Sorry. That's going to run into D. Is that right?
Yes.
Because all I'm doing with the lithium and ammonia is a reduction. Right? It's a way to reduce the alkyne down to the alkene. Yes or no? Is anybody not following or not seeing that?
I see it.
All right, good. Do you feel more confident now since we're going through it one reaction at a time?
Yes, I do.
It should start clicking. Oh, okay, this is okay, I see it now. It should start clicking. All right. So now we've done almost this whole reaction scheme. took the whole class, but I expected that. What about E? So this is D. Everybody agree that this is, let me change the color on that. That this is D right here. This is the product for D. All right, D is ragged. Everybody agree with that?
Yes.
All right, I'm putting lunch on the line again. Going from D to E. All right, keep in mind, I'm not doing anything with that initial alkyne. I'm done with that. So every reaction, every subsequent reaction is going to be on a different start material. All right, so what about going from D to E? What am I doing there?
Will you create a carbonyl,
Who was that?
Kayla?
Oh, I didn't hear I couldn't hear your accent when you said carbonyl, but I heard it when you said your name though. You're right. So what type of carbonyl? So first let me back up and slow down. Tell me the name of the reaction and tell me what happens. And then we'll discuss the products.
Ozonolysis.
Is it
That's
osmolysis?
Yeah.
We both screwed that up.
Yeah, that's all right. That's all right. I'm gonna write it out. Write it out. It's ozonolysis.
And then doesn't it like break in the middle, and then those two
Yep.
keep them.
You're gonna basically, without going through the mechanism, because this is a very long mechanism, we're gonna take that alkene and do this. Crack it in half, right? And each carbon, let me put the carbons back in too, because I don't want you to lose sight of that. Each carbon in the alkene becomes a carbonyl. What type of reaction is it? Is that an oxidation or reduction?
Oxidation.
Oxidation.
All right, so right here, what you're going to get out is this. That's one of your products, plus what? Really the same thing on the other side, but that's all right. We're going to make it work. Am I right with that?
Yep,
Ah.
looks right.
Sorry. Right, those are my two carbonyls. Anybody disagree? So this is the answer for E. It looked like a lot at first, didn't it?
Yeah.
Yes.
But we whooped it. Right. Sometimes things look bigger than they are. But that's when having confidence comes in. Say, it looks like a lot, but I think I can handle it. All right. So we're gonna stop there. We got 2 minutes left. I'm gonna leave that open for questions. If anybody has any questions.
Dr. So I don't have a question, but I wanted to tell you, like, as a student, you're really a great professor, and I appreciate your efforts during this pandemic with us. You've been really patient and a really good professor.
Thank you.
I want to tell you that.
That means a lot.
And I second that.
Me too.
I second that as well.
Like I don't think.
Yeah, I think
I just wanted to tell you that because I feel like you need to know that as a student.
I appreciate that. That means a lot. I give God glory for it too. I appreciate it. Thank you. That just made my day. Now I can drive to Tuskegee and be smiling the whole way.
Great, I'm glad.
Yeah. Now, seriously though, I think with the conditions that we're under, y'all have been doing pretty good too. Y'all been doing excellent. As far as staying up on top of your stuff, asking questions outside of class, emailing when you have questions, and being proactive about your learning, like that actually matters. You know, I was looking at an email chain the other day. It's something going on in another class, but sometimes you have people emailing teachers and stuff like that, and they don't expect any responsibility to be on the student. They expect it all to be on the teacher. And it can't be like that. It's a mutual proposition. I got to do my part. You got to do your part. And y'all have definitely been doing your part. So I appreciate that too. It's been a good class, even though I can't see you and we ain't cracking jokes in the classroom, stuff like that. It's been a great class. And we're not done. We still got a week left because we get out on the 17th. So we got one more section to cover too, which I think is going to be awesome because it's going to be pretty fun and easy too. I always like to end on a high note. But yep, I appreciate that. Means a lot. Yep. Any other questions? Anybody got any questions after the love fest that just happened?
The love fest. I have a question.
Go ahead.
So this is for lab.
Mhm.
Kind of, yeah. So like the worksheet, the lab worksheet we're supposed to do, I think we're all kind of confused on when we turn that in. Like if
Oh
we're
yeah, don't turn it in yet because you got to get your pure yield.
right.
I
That's
got to weigh out the aspirin and give you those numbers.
mm-hmm.
Yeah, so don't turn. I had a bunch of people turning in early. I cleared them all out because you need the pure yield and you need to calculate the percent yield, which you can't do without the actual yield.
Okay.
So just hold tight, and
Okay.
I'm
So
gonna
will you do that to us this week, or will?
I'm gonna post the numbers today when I go to Tuskegee.
Okay.
I'm gonna weigh everything out myself. We don't have to have a Zoom session for that. I'm just gonna weigh it out, record the numbers, and I'm gonna post them to Blackboard.
Okay.
And what you can do, because I know the group thing at first sounded like a good idea, but I still got people saying they don't have a group. So what I'm gonna do, I'll just post the numbers. Whichever number you want to use, just use it as your pure. I'll put the names of the people who were working, and that way you can, if it's somebody on Tuesday and you in Tuesday, you can pick one of those numbers. Or if it's somebody on Wednesday, you in Wednesday, pick a Wednesday number. But either way, those numbers will be posted today. And then I posted that video Monday dealing with the NMR. So make sure you do that assignment too. And then we will have a lab final. It'll be open notes on Blackboard, but it's going to be a short exam, very short exam. As a matter of fact, we'll probably do the final next week and get it over with.
Sounds like a plan to me.
Yeah, it is a plan. Trust me. The faster I get done with those labs, the better. Because those labs, even though they're only one day a week, that's a lot to prepare. It's a lot. It took me like 3 hours to make that video the other night.
Wow, that's dedication.
3 hours to make it. Well, 17 minutes to record it, and then 2 hours to edit it. So.
Good. You work well with the videos too.
You're a real one, Dr. Russell.
Yeah. So we're gonna stop here. It's 12:02 Friday. Come ready to work because I'm gonna cook up some questions, and you'll be working in breakout rooms, working together as a group. And then every question you submit that's correct, you're gonna get points for your group, for your whole group. So
Okay.
that should be pretty fun. It's gonna be kind of weird because when you're in a breakout room on Zoom, the professor is not in the room. So y'all just gonna have to get it how you live until I bring everybody back together. But it should be kind of fun though, because it'll give you a chance to work with each other and and bounce ideas off each other. But I gotta cook up a few good questions though, because I don't want it to be too easy. All right. So I'm gonna see y'all Friday, God willing.
All right. Bye, Dr. Russell. Enjoy the rest of your day.
All right. Take care. Cook it up. That's right.